Hello, how are you doing? So let's take a look at Canvas. We're going to cover Unit 7 today. I hope everyone's doing well. Okay, we should check out our assignment. I'm good, thank you. Okay, good. So if you have class on Friday, we have a holiday this Friday for Cesar Chavez. So no school on Friday. Let's check out our notes and our assignment. I'll go over that right now. Okay. So for today, we're going to dig a little deeper into the LC-3 coding. I think as we were doing the lab, we're trying to get used to the instructions. So the assignment that we're going to do today is going to review some of the opcode and looking at the instructions and how to really read the code. I think some of you are doing really well in writing your program and understanding the code. But we want to also continue to practice, okay? So let me zoom in real quick here. Let's start from the beginning. So today we are going to cover chapter 7, and chapter 7 is going to allow us to understand a little bit more on LC-3. And at the beginning of the chapter, it talks about assembly language. And so we learned that ASM is a low-level programming language, and we have various type of ASM. And as you assemble your program, when you work on the lab, you see that we're using the assembler. And so an assembler is a program that turns symbol into machine instructions. Some of our symbols can be opcode, like your add, your load, your store. That's your opcodes. Some of the symbol will be your labels, right? Like we would see our labels using a certain name like X, Y, or it could be start, things like that that we've seen in the lab. So labels really refer to a way that we identify our memory location, where things are stored. And with that, it uses the memory locations for operations such as reading data or saving the data or writing the data. And it is just a human way of referring to a memory address right inside your microprocessor. Now, if you're looking at ISA, it is really corresponds to the type of symbols that we're working with. And so our symbols are made up of instructions or your opcode and labels. In most assembly language, this is what you see. You see that symbols can represent a set of instructions that's allowed in the syntax for that language, and also a way that we can refer to where your data is stored and accessed. So in this example program, what we see is we're going to see something like this in our lab this week for multiplication and division, similar to this. But in this program, what we see is we are going to multiply a number by a constant 6. And we have several ways to really approach this. One way is we can bring in the integer as a hexadecimal value, or we can fill it by initializing a certain label with that value. And that's what you see in this program. So now the program here, you see that it uses a different origination address. This is not common for us, but you can start your program at a certain location like this. Normally, we would do it at 3000 because that's the top of your simulator and we would have more room to work with if we started at the beginning of your address array. So we have the origination address, then we are going to load the label 6 to register 1. And then we're going to load the number label to register 2. And then we initialize register 3 at 0 or clear it because we want to get it ready to store value. So here you're going to AND register 3 with the 0, and that's going to be 0 for the register 3 as the destination. So as you look at this program, what you see is you see load, LD, you see AND, right? And that's your opcode. And you also see labels, 6, number, again, right? So for the loop here, what you see is that we have a loop incorporated, and that's going to be using the label again. As we clear out register 3 in the previous line here, what we're going to do is we are going to take the number label, which is at register 2, and we're going to add it to register 3 and store the result in register 3. So register 3 is really going to be whatever that's in the number location added with 0, which is we previously initialized. And as we're looping, we need to have a way to count our loop, right? We can count up or we can count down. And in this case, we're going to decrease. So we're going to subtract 1. And so we know that we have 6 is the maximum value. So as it loops through, it's going to be 1 less. So you're going to subtract 1, that's 5, and so on. So what it's going to do is going to keep adding 6 times, because when we multiply by 6, it's like adding the value 6 times. So as we're looping, we continue to loop, we're going to subtract 1 each time. And we're going to branch it back again to the beginning of the loop when it is positive. So as you subtract, so if I have 6, I subtract 1, I have 5, and then it's going to come back up again, and it's going to repeat the process. And then I'm going to be down to 4, 3, 2, 1. And when it gets to 0, right, it's not going to go back to the loop. It's going to halt. It's going to go to the next line. And so this is how we can implement the loop, where we can have a way to count it down. And it's going to check the register 1 for a positive value. So it's always going to go to the previous line destination register, which is register 1 right here. It's going to check. So if register 1 has a positive value, it's going to come back to the again label. If it is not a positive value, like a 0, then it's going to go to the next line. And if you look at the data section, in the number label, we assign it 1 block word. And we know that a word is a 16-bit. So when you give a 1 value here, it's going to use 1 block word, which is 1 16 bits, right? 1 word that represents 16 bits. So you can do it this way to cut up a section of memory, which is 16-bit, to use for this label number. Or if you give it 2, then it would represent 2 block words. That means that it's going to take 2 of the 16 bits to dedicate to a specific label. And then we have the label 6. We fill it with hex 6. Hex 6 is equivalent to decimal 6, as we want to multiply by the constant 6. So this is how we would do the fill. So when you fill here, right, and you load it to R1, this is going to be treated as a counter. So we're going to count 6 down. So as we go for each loop, we're going to subtract 1. So 6, 5, 4, 3, 2, 1. And once it hits 0, it's not going to branch anymore. It's going to go to the next line. And this is how you can implement multiplication of a constant. Any question? Okay, so let's go and answer some question. I use the same example that you see in your notes, right? You're going to refer to this example and you're going to go ahead and answer the questions A through D for number 1. So for question A, it asks you to identify the instructions, the mnemonics of 4 opcodes in the program. And so when we look at an instruction, we look at what is it doing, right? Specifically for the opcode, the register, and the labels. So right away, when you're looking at the beginning of the program after the origination address, the opcode is the first part of your instruction here. Like the LD is a load, and we know that load is to read, right, data at a certain label. So we're going to load that to the register so we can access that data. So LD is an opcode. If we go to the third line, we would see AND. So the operator AND, and in this case, our instruction AND, which is the opcode. And this would allow us to clear out our register 3, right? We clear or initialize that register 3 at 0 so we can start storing value to it later on. And then in the loop, we see add, right? This allows you to bring in value or be able to operate addition for the values in the registers. So we took whatever's in register 2, which is loaded with number label, added with register 3. And so add is an opcode. After add in the loop, you also see BRP, which is branch positive. And this allows us to use, right, the condition positive or the flag positive to check against the destination register from the previous line. If the register in the destination register, which is register 1, holds a positive value, that's true, it's going to branch to the label. So BRP is also an opcode. And for the pseudo instruction, which is your halt, right? This is more on directive because it is system related. So on the low level, when you see halt, see, get C, in or out, those are directives. And so that's specifically assigned to operate on the hardware level. So when we halt, we stop execution. When we do get C, we obtain the value from the keyboard, right? When we do out or puts, we display on the console, which uses the monitor. So halt. And halt is a pseudo instruction because inside the halt instruction, it actually uses trap, right? So the opcode for that is trap, but the directive or the pseudo instruction is halt. So what I want to do in this is to really go through and identify some of your opcode, which is what you see. That's the first part of your instruction on each line. And then we need to identify the label. And this should be really easy for you as you've seen labels before. We can see label in the data section where we do the fill, and also the label in the case where we use it to implement loops or a certain criteria, conditions, and so on. So we see number, which is, it uses a block word, one block word. 6, which is a label, and we use it to fill with a hex value. And then again is used as a label to be able to apply the loop or the iteration in our program. And so we can quickly do this by looking at each line or our code as an entire component and seeing how this will work, right, together and individually as each line of code. So for the final exam and future quiz, right, I expect that you need to be able to understand snippet of LC3, even though we have it as multiple choice. I will give you the options that you need to select to really understand what the lines of code really represent, right? What's the value in certain register? What are we doing there, right? Is it a loop? So making sure that we understand how to write it and how to read it is very important. Then for C, we just need to identify the register that's used. And I emphasize this in the last few labs that yes, you can use any register, right? Some registers are specific for certain things, like register 0 is used for in and out or get C and puts. For input and output, we use register 0. And register 0 also is used for LEA when we need to prompt a string. Okay. But when you use other registers to operate, right, or to copy or to do things in your program, make sure that you track the register. If I load my register 1 with the label, I want to use that to be able to do something in my program. And in this case, we implement it for the loop. And we would use it to decrease in our loop as we loop through. So in the iteration, we implemented the register 1, right, for that. Register 3, we also initialize. So for our answer, we know that there are 3 registers being used, R1, R2, and R3. Now you can reuse the register by clearing it in the next part of your code, right? You can use it for one section and then you can clear it for the next. Or if you don't clear it, whatever that's remained in that register, you can reuse it. In the case that if we need to retain some data from it, we can take that to another part of our code and reuse it. If we want to really see the value, then we can store it out to another label or the label that we define. So that way we can see the output. So in this program, we use register 1, register 2, and register 3. And then we know that comments are ignored by the simulator. And in LC3, we use a semicolon. And that is varied in all programming languages, right? So you want to check the criteria on how comments is used for each of the type of language that you're working with. And so when we're looking at the comments here, right, we have comments. R1 keep tracks of the iteration. Unfortunately, LC3 doesn't allow you to do multi-line or block comments. So you just have to do it like this. One using a semicolon and then the next one using the next semicolon. So I simply put down some comments, right? Clear register 3 or R1 for iteration. And you don't have to comment every line, right? By practice, we want to comment something like this, the inner loop, to really represent that section of the functionality of that code section. So it's a really good practice to be able to be clear with your comments so that way when someone else is reading and testing your code, they can quickly go to that section and take a look at what you intend to do there. Okay. I normally, in the beginning of this class, I comment every line to help you understand what each line does. But for the project, I expect that you do add comments for your code, but it doesn't have to be every line. It can be the various section in your code. And, you know, part of your grade is to be able to put together a working program with all the required elements. Any question? Okay, so back to our notes. And so when you go through the program, you would need to first look at what type of instruction that you're working with, what kind of directive or pseudo opcode that you're working with. Like we talked about halt, right? It uses trap. Or when you see like get C or in or puts, those are the assembler directive or pseudo opcode. And then, you know, look at the comment to really see the intention for that section of code or what it means. Now, as far as syntax, white space between symbols and the case sensitivity is ignored, right? In this case, we are okay with upper lowercase. Normally in LC3, you type in capital letters or uppercase. It's just a practice for assembly. When you program assembly, you know, it's easier to read when everything is capitalized. That's just how we normally do things. I do see once in a while, you do see some program that they use lowercase, but it's a little bit harder to read. The only time that we treat white space specific is in the last program that you see, right, when we did the day of the week, because it's using the array of memory. And so if you're one character off, right, it's going to push everything else out of order. But in general, your white space doesn't matter. So you can make it where you tab it and align it so it's clear for you. So it's easier to read if you align things. And that could be varied from, you know, your text editor on how you use it or how you type it. So whatever makes it easy for you. And so you've seen this before. I took this from a prior note. So you would see label goes before opcode. And opcoder, we talked about add in, right? Not, load, store, depending on what you're trying to do there. And then operands are normally your registers, your immediate value. It could be like a decimal or a hex, or it could also be a label that will fall into operands. And then your comment should follow by a semicolon. And so here are all the operands information. And it is comma separated, so you would use comma to separate each of the component. And so we already talked a lot about label and how we use the label. And label can be used in many different ways. It's really depending on how you see the solution for the problem. And so I normally would use a label that would represent the functionality, or it would have some meaning that's related to my code. Very similar to what you've seen, how you declare your variable, right? In C++ or Java or Python, it has to have some kind of meaning. If you use a certain identifier, like, you know, you create a function name or you declare a variable, you want it to be represented of, you know, the intention for that code. Okay. All right. So here are some of the tips for your comments and the purpose of your comment. All right. Any question? Okay, so let's go to number 2. It says refer to the format image and provide an example that contains all components of assembly. So by this time, you should be able to write at least a couple of lines, for example. I need to have label, opcode, operands, and possibly some comment. So we can use various labels, like label can be positive, negative, number, loop. Your opcode could be add, not, load, store, LD, LDI, BRP, BRPN, BRPNZ. Your operands could be registers. It could be decimal value. It could be hex value. It could be a label. Some of the comments that you might see, we can load a label to a register. So the example that I put down is I have a label called POS. And I take register 2, I add it with register 3 and put it on register 1. So at the POS label, register 1 is register 2 added with register 3, and you can do other example. I also have another example. I have the label called begin, and this is what you see in the last program that we did, right? We have a start or restart. So begin, and I would load my prompt to register 0, and I know that prompt is going to be a string because I'm using LEA0 here, right? And then right after this, I would use a directive, which is puts, okay? So the purpose of this is to prompt user on console. So we can continue to explore or put down different example. It's really easy. Any question? Okay. So let's talk about pseudo operations, and these are known as assembler directives. Okay. So your original address, the opcode is ORIG or .ORIG, and we would follow that with a hex value to represent the address, like hex 3000. So that's going to be the starting address of the program. Now, pseudo operations do not refer to the operation executed by the program. It is used by your assembler, and it looks like the instruction, but the opcodes start with a dot. So you would see the dot, right? Dot fill, dot block word, dot end, dot strings. And dot end, we know that it is the end of the program. I mentioned the block word already. So BLKW, dot BLKW, and you would follow that by a numerical value, right? 1 or 2 or 6. This N represents the number of block words that you are allocating to that particular label. So instead of doing a dot fill, right? Fill, I'm limited to 1 block word or 16-bit for that particular address or value. So if I fill it with a hex 6, what that does is giving me, right, that 16-bit for the hex 6. But when I do it with the block word, I can group them by using a numerical value here to represent, you know, the number of words that I can use allocated to that particular label. especially when we use a larger value or we want to do something like an array, um, where we would have a group of values that would be stored. It would exceed a certain number of bits that would represent it in for the immediate value in the instructions. So we can do it this way. And then strings, we know that it's null terminated. We talked about that before. So it's n+1 location. Each of the character, it's going to allocate one word. So we can actually use this to be able to put together a number of characters that represent a string, or what we see as text for the human. So here what you see is your pseudo operations. Those are the dot at the beginning. Your pseudo instructions are the ones that I mentioned before, like halt. These use traps. So the opcode equivalent is going to be trap with a vector. So it's going to use a hex value to execute that. So when I do a halt, it's going to execute the trap instruction with the vector 25. So this is just a number, a numerical value or numerical vector that's assigned specifically for that directive, right? So when it terminates the signal, it does the trap vector 25. When I tell it to record an input by using in, so it's going to print prompt on the console and it's going to read a keyboard character. It uses register 0 for that, right? So when you're doing an in, it's a trap vector 23. We need to remember this for our exam and our quiz. So for the pseudo instruction out, when we're displaying on the console and that's passing through register 0, it is trap vector 21. Get C, right? If you notice, if you compare in to get C, they both use one character, but in prompt on the console. Okay. Get C, read a character from the keyboard, and it's going to store that in register 0. So as I mentioned in the last lab, and I answer some of your questions when you guys email me or come to my office hours, register 0 specifically used for input and output. When you are obtaining multiple character, you need to make sure each time that each character's input gets moved. So if I want to type in 2 characters, like the number 12, I would first have the 1, and then it's going to go into register 0. Then I need to copy it to register 1. Then for the second input, which is the number 2 to represent the 12, it would also come into register 0 because the 1 has already been moved, right? Register 0 now can have the updated second input. If you don't move the value, it's going to override. So if I have 5 characters as input, I got to move it 5 times. And then we would ASCII convert it to treat it as numerical value by subtracting, right? We can do it with hex or decimal. And then we do the operation, we use it in our code, and then before we output, we ASCII convert it back by adding the offset, right? Either 48 decimal or 30 hex. So get C uses trap vector 20, and that's to record 1 character input. If you do a puts, this is to write a string. Okay, puts is different than out. Out write 1 character, puts write a string with null termination. and the address of the string is in register 0. So we normally use LEA and then puts, right? Because LEA allow us to load directly from the actual address, so it doesn't use the PC for that. Then we do a put, so it's going to display the string. Okay. Any question? Okay, so make sure we know this. I'm going to repeat some of this later on, but for the purpose of exam and quiz, we got to understand the difference and understand how it's using trap for your pseudo instructions. So the next part talks about your style guidelines, right? What you should include in your assembly program. It's always a good practice in all programming language to kind of give, right, your code evaluator or whoever that's working on your code an idea of who wrote the program and what the program intend to do. And I think you saw some of this at the beginning, right? Expectation at the university level, they're going to expect you to know the best practice in programming. So it's always good to kind of carry that out in this class. And we want to kind of align things so that way it is easy to read. So you start with the label, then you do the opcode and operands. And if you keep it uniform, it helps you when you debug, it's a lot clearer and you can see it. And when somebody else debug your program, it's clearer for the other developers. All right, and then use of comments, use of symbolic names that represent, right? You can also mix upper lowercase if you like. And then provide comments between sections. Okay. Just make it as aesthetically pleasing. All right, let's look at the next part for our assignment. So here's a program. It's similar to the last program. This program, if you read it, you already know that it's a constant 3 that we're multiplying, right? So I want you to go through and you're going to start from line 1 and you're going to go to the end of the program and you tell me what each of the line means. So for the first section, part A of number 3, it asks you to describe line 1 through 4. So for line 1, we have .orig, which is our origination address. And this is your pseudo operations. So line 1, I put origination address at hex3050. This is the start of my program at hex 3050. So when it loads your program, this is going to be the address where it starts. Remember that this is low level. You got to tell it where it's going to begin with the setting up the memory location for the operation for your program. For line 2, we look at the load. So this is an LD, register 1, and the label 3. So for line 2, I load register 1 with the label 3. My label 3 is the operand. My register 1 is the operands. And LD is my opcode. For the next line, line 3, we have LD R2 number. And that line means that we're going to load register 2 with the label number. That means that it's going to go to the number label, which is a memory address, right? And it's going to tie that address to register 2. That's where we're going to be able to read the data. Then we're going to have line 4. And line 4, we have an and. And R3, R3, 0. So my operands are R3 and the decimal 0. My opcode is register 3. I'm sorry, and my other operand is register 3. So this is a way that we can clear register 3, or we initialize register 3 with the decimal 0. Any question? Okay, so for line 7 through 9, and in this one, just like the first example, slightly change, I have the label again, and then I have add R3, R3, R2. So for line 7, we're going to enter loop labeled again. We add register 3 with register 2 and store the result in register 3. So if you look, just like what we explained earlier, register 2 is number. Register 3, right, we initialize at 0. And number is filled with a block word, one block word. Okay. This is a way for us to, as it add each time, right, it's able to add the value into that section or the 16-bit one block word. So that way, when it loops through, it's going to update the value so we can write it to a certain location, which is called number, and it's 16-bit. And when we loop, so the first time it's going to add the value, it's going to place it there, right? And then the second time it's going to update that value and it's going to place it there, and so on. And then for the next line, line 8, add negative decimal 1 to register 1 to reduce the loop count. And this is a way that we decrease, right? We count down on the loop. Because register 1 is loaded to the 3 label, so, and we fill it with 3. So this is it's going to loop 3 times. And each time we're going to start with 3, we're going to count down. But you have to think of it like in a memory location, when you decrease, you're going to move down 1, you're going to move down 1. So as it execute, it's going to move to the next location and so on. So we're going to decrease 1. That's how we're going to keep track of our count in our loop, is by subtracting 1. And then for 9, we're going to branch if positive. It will re-loop, right, as long as R1 contains positive, right, after subtraction. As we subtract in the previous line, right here, we add the -1, which is subtracting 1 for counting down. Whatever the value as a result. So if I take 3, subtract 1, I have a 2. A 2 in the destination result, it's going to check for positive. That's true. It's going to come back to the again here. And then when I get to 1 subtract 1 is 0, it checks false here. It's gonna go to the next line, halt. So I put for line 9, branch if positive, it will re-loop as long as R1 contains positive value after subtract 1. After subtracting 1, return to again label. And then for the next line, line 10, which is empty, and 11, I should say 11 here, right? So my else is otherwise exit loop or halt execution. So as we talked about how it checked false for the positive, when it gets to 0, it's gonna not jump back to the again, it's gonna go to the next line, which is halt execution. And then for 13 and 14, we talked about this extensively already, right? This is our data section. So for line 13, we're going to allocate one block word for number label. For line 14, we're going to fill the label 3 with hex 3. So label 3 contains hex 3. Any question? All right, pretty easy. Okay. So this is what you see in the presentation, and also if you refer to the book. This is like some of the example that we've been using in the lecture. This is a program that counts the character in the file, right? And the way that they laid this out is you when you go through the process, you want to be able to initialize, so we count at 0. This is when we're going to implement the pointer that's going to be the first file character, right? And so when you see it at the low level, you're going to see that, oh, when it's doing an input for the keyboard, that's a trap vector 23. And then we're going to load your character to file. So the register 1 is actually having the memory address that was tied to register 3. Okay, so you need to be able to add that and store it back to register 1, and so on. So we kind of need to map it out on how it's tied to memory location for the register, connect using the register with the label or the memory location, how your pseudo instructions is being used, and then also how that is going to be transfer from one register to another, so that way we can do the operation. Now, if you look at this here, they're not using the register 3 directly, because even if you load it to a location, the reason why they're doing that is that if you transfer it to another register, like let's say we did an operation by an add here and put it onto destination register 1, right? We can use that register to branch. If you branch from here, there's likely that, because you didn't do any operation, it's not going to work. So you need to operate it by using an add or whatever, and then to be able to branch. So it's going to check the destination register, where it's going to be able to check for positive or negative. Okay. So ASCII conversion, then when they do a match, this one we do an increment in the count. So the register 2 is going to be the counter, and then how it's going to load the next one. So ultimately what we can do is we can store it back, right, to the location of register 3. That's going to be our final result. Okay, so in LC3, this is what it would look like. Now everybody approach it a little differently, right? So you can take a look at how we initialize the value using the PTR or a label called PTR. Okay, so let's do the next exercise now. So I took this program. This should look very familiar to you because this is your prior lab. Okay. And I want you to identify the assembler directives in the below program. And remember that assembler directives are made up of pseudo operations and pseudo instructions. So we would start with the operations. So we would get to the first line, which is .org. That's a pseudo operations. And then you see .strings, .n, and .fill. Not necessarily in that order. I'll switch it around. X. Okay, so the dot in the front are your pseudo operations, and that's considered assembler directives. Where your program start, where your program ends, how we fill the strings, how we fill values. Dot strings, dot fill. Then we can let's put down some of your pseudo instructions. And here you would see there are quite a few, right? Your puts, your get C, which is in the next part. So puts, get C, and halt. And if we want to take the pseudo instructions and we need to break it down to our trap instructions or trap codes, puts uses trap vector 22, get C use trap vector 20, and halt use trap vector 25. And we're only looking at those because they exist in this particular program, right? There are others, as we saw in the table. Any question? So the idea is to let you identify, right, what is a pseudo operation and what is a pseudo instruction, which is made up of your assembly directive. And those allow us to start and end the program and then be able to add data and initialize data in our program and then have input and output and stop execution. Any question? So next, let's talk about assembly process. And as you use your simulator, right, let's say that you use the editor in the application or another text editor that you have to write your program. We save it as a .asm. Okay, that's a must. In other assembly language, it's the same. You have to save it as a .asm. Some assembly language uses C compiler. So in order to build the program, it uses a compiler to interpret, right? As it goes through the compiling process, it's going to interpret the label or the symbols that you put in your code. So all the coding that you do in assembly is basically, right, putting in symbols, which consist of instructions and labels. So in LC-3 in particular, right, this is a standard practice for assembly language. In LC-3, it's gonna, when we put it to when we use the editor or our online simulator and we assemble the program, you see that it creates an executable file, which is an OBJ, a .obj. This is used by the simulator to simulate the program for you. And so if you have Windows system, you use the application, the simulator that comes with the textbook, the LC-3 simulator. You can upload the OBJ to the online simulator and it should be able to run, right? They built the simulator to accept the executable file for assembly, which is the OBJ. So your assembly language program, it's going to go through two passes. The first pass, it's going to take your code and put it all your instructions. It's going to break it down and it's going to store on label in one section and then instructions. So it's going to put it into the symbol table. And then for the second pass, it's going to take those symbols, right? And it's going to convert that to and include that in the executable file. So that describes it here, right? So the first pass, scan through your file. It finds all your labels. That's why we put the label first. And then it calculates the corresponding addresses. Some of it comes from the PC, your program counter, and then some of it is, a lot of the time the labels are tied to the fill or the block word. So it's gonna look at where that address is. So basically it's finding the actual location for the label. And it's using the symbol table as a reference for those locations. And the first thing that you see is the .org, the origination statement. That's going to be the first instruction. That's the location for the first instruction. So with that, it uses the LC to be able to track your current location for the program counter. And then when there's a non-empty line, if the line contains the label, it's going to add the label to the table. And it's going to keep track of the location of that particular label, the address of that label. And then it's going to move down, the increment, it's going to move down to the next line. And that's how it's able to build out the symbol table. So in the case that if you have the block word or dot strings, right, these are your pseudo operations. Instead of increment in the LC, it's gonna actually use the number of words. So if I put block word 2, it's gonna increment by 2 because there are 2 words being used for that particular label. Or when I have strings, if my string has 10 character plus the null, that's 11, it's going to increment, right, 11 words for the entire string. because there's a null termination, right? 10 plus 1. And then it's going to stop when it reaches the .n. So this is happening in the background, right? When you load your program, or I'm sorry, when you click ASM, right, you assemble, it builds out the table before it spits out your executable image, which is your OBJ. And then on the second pass, it's going to convert all your opcode and your operands. And so that's how it's able to make that into your binary, right? That's what you see on the left of the simulator, the 0 and 1s. That's through the second pass when it assembles your program. Okay. If your operand is a label, it's going to use the table to look up that address for that label. Okay, so create the reference table and then use that table to operate the instructions there for the executable image. Okay, this is wrong, right? We do not R1. This one's missing the third operands, right? We cannot add a label this way. So we load and then we add. So these lines are wrong. When you have a value that's too large, it's also going to throw an error, right? Remember that we are 5 bits for immediate values. So if it doesn't convert and fit in the 5 bits, you have to break it into multiple instructions. Address of labels that is more than 256 locations or instruction later, it will not find. It has to be PC relative. So don't put it too far. Okay, so when we fill, we want it to be within that 256 or 255. That's ideal. All right. Okay, so I think we already answered that one. Let's go to number 6. What are some of the guidelines for LC-3 programming? And you can take what I have in the notes and put, if you want verbatim, or you can summarize it, right? We want to put your program information, possibly author's date and purpose of the program. Some professor at the university, they would want you to indicate what's input, what's the output, what is the expected output, if there's any kind of side effects, things like that. They're very particular about certain things that go into the program. So always making sure that, you know, that's meet the criteria, right? And you would want to treat your client the same way. If you build your program for your client, you want to see what they want in the program, what kind of things they're looking for. So having those things is ideal. I am particular about GitHub README page because I really think that you should follow the standard, right? On your GitMe page, I need your information, who wrote the program, when you wrote the program, what version of the program, and the purpose of the program, and if there's install or run instructions, you need to put it there, right? I have a lot of projects that get turned in, and then I have README page. It's like, you know, LC3 project or CIS11 project. And that will not do with the industry, because when you submit your GitHub information to employers, and if they look at your project and if it's not standardized, it just look like me as a professor, I'm not preparing you for the industry. Second, you're not prepared to be a developer. So I want to make sure that you understand that certain things that we require, it's not because it's busy work, it's because we want to make sure that you follow the standard, you follow the best practice. Okay, so putting things in, I know it's extra work, it's a little bit of typing and formatting, right? For GitHub pages, it's HTML format, but that's going to be with you for a long time. So making sure that you maintain your repo is very important. Use comments, make sure that it's explanatory, make sure it's meaningful in symbolic names. You can mix upper and lower case, or you can use all cap. It really depends on what your preference would be as far as identifier and labels. Okay. And then comments in program sections, and then making sure that if it's overflowing the line, then we want to make sure that there's no wraparound or truncations. So it's just aesthetically pleasing. We talked about the process. So what type of files are created in LC3 editor? So when you use the application, I think some of you are not, right? You just use your text editor and your online simulator, but by default, when you save your ASM program, when you assemble, it's going to assemble these files. Your .bin, which is binary, .hex, which is hexadecimal, .sim, remember we just talked about the symbol table. That's where your address and your labels are associated. .lst for list, which is used to list your instructions at the low level. And then your obj is your executable image file for simulator. Now, some assembly language uses emulator, and then, like I mentioned before, some uses compiler. I think more of the, some like ARM 64-bit, some of them uses, because there's different version. With ARM, some of them uses emulator and some of them uses C compiler. And when you use C compiler, you can simply use Visual Studio. That's probably the best way. And then what you do is you're going to link it. So you have to go in and edit, right? Configure it to link to specific package that is for that assembly language. Otherwise, it will not compile. Like, for example, if you work on Microsoft ASM, right, you can link it to a specific package for that version for Microsoft ASM. Like for x86 or something else. Okay. So this is a type of files that when you click ASM, you would see these generated. For B, number 7, what type of file is used to simulate the executable image? We talked about OBJ. This is your object file. And if you assemble and you have the OBJ file, you can upload it to your online simulator, right? I tested it and it worked, right? You can simulate on with the online simulator with the OBJ. Now, in the case that you don't have the application, if you're using Mac OS and you use your text editor to write your program, you have to open the assembler, you copy and paste your code, and you use the online simulator to build, right, to build the object file directly there. Okay. And then for question C, it asks you, during the assembly process, what is used to maintain program labels and addresses? And we just talked about this. You saw the diagram in the notes. It is the .sim file, which is your symbol table. That file in particular contains your labels and their addresses. And then for D, what type of statements will increment the LC during the assembly process? And we would see this with the pseudo operations, block word, or dot strings. We talked about this just now. The N value following the BLKW, right? Let's say I do BLKW 4, that's going to be 4 block words or 4 words allocated for that particular label, then it's going to increment that in the LC. For strings, if I have 5 characters in my strings, then it's going to do 5 plus 1 for the strings. 5 plus 1 words, which is 6. For number 8, we need to identify the issue with syntax here, right? Add R1 with decimal 300. This is not doable. It is immediate value is too large. And the same thing with negative. Okay, so for 8B, negative 260 decimal, that's still too large. So in order to operate this, I have to break it up into multiple instructions. So I have a few lines to be able to handle 260. Just like how we did the ASCII conversion, we did 48 in 3 lines or 4 in some case. It really depends on how you want to do that. And then for the hex value, this is also too large. And I put my recommendation for this is when you use it like this, yes, you can break it down into like multiple lines, but it gets very lengthy and you have to also track it. So it's good that we would do a dot fill instead to a label and then load it to register 2. So I would do, let's say I would do address 1 and then fill this with that address 1 and then load it to register 2. And now I will be done. So 2 instructions. Any question? All right. So here we see the visual for that, right? When you put it through the assembler, the files. And so when you look at your simulator, right, each of the binary line represent your code and instructions, because the simulator intends for you to see things as what the microprocessor or your computer sees it. Okay. In this class, we see things as what the low level would be. So your machine instructions like this. So one of the important things that they know in the text and also the highlight in the presentation is that your object file doesn't necessarily have a complete program. Okay. It really is a way for us to be able to use routines, which is low-level functions, and to be able to allow us to include blocks of our code to be able to implement that in our program. So the practice for this is you can load your program between hex 3000. We always start there in this class, right? You can do it a little later. And it has to be before this address, FDFF. That's the end of your program address. This is the last address, okay? We don't load here, we load before that. So anything between here, we can start at 3000, we can go from there if it's very lengthy. Each of your object file needs to have a starting address, right? Your simulator will not allow you, well, when you assemble, it will not assemble without a starting address. Almost all assembly program, you would see that it has some way to start. Like you're going to tell it, begin here. That's the address, okay? And then also in the case where you're working with multiple files together, and we'll talk about linking shortly, do not overlapping object files. You cannot start at the same location, okay? Because it needs to section the memory to be able to build out different files. So when we're loading, and we're talking about loading the object file, the executable image, when you click load program in your simulator, this is a way for us to copy the executable image into the memory. And they mentioned that in other form of loaders, you would have a way to relocate the image to fit in the available memory. So it would adjust because your memory is dynamically writing. So it would be flexible to be able to adjust based on the storage that you need for your application. And so it would readjust based on your branch targets by looking at what is in the symbol table for the load and store addresses. Okay, and so this is, what you see with the later assembly language where it is flexible in how it's using memory allocation for your application. Now, linking is a process that we would resolve symbol between independent object files. Very similar to what you would do in C++ when you do include. Or in Python, we would have import, and other languages, we would do an import. A lot of times we bring in a module or a package or a file, right? In C, you would do a .h, right? File as a third file or a third-party file that could not be part of your programming language package. So let's say that you wrote multiple program and you want to modulize them and make them work together. So it is a way that we can link them, or in the case that you found someone's assembly program and you want to incorporate that, use that as a library, right? So we would link it. And the way that we use linking is we use a pseudo operation called .external, and this is the same in most assembly language. Okay, you would say .external, and then you would say the file name, or in the case that if it's not contained in the same folder, then you have to put in the path for it. I would suggest that it's best that you download the file and store it within the same folder of your program file, so that way it can find it. If not, you have to set it up. Like if it uses a C compiler, you have to go in and modify your configuration to link that particular file. And then in your code, you have to say .external file name. Okay, just like how we say import, and then the module name or the package name. Okay, so this is a way that we can use another module that would use the symbol from another module to work with our code. So for example, someone had written a program and it has the proper labels and all of the values that I need. Instead of rewriting it, I don't reinvent the wheel. I bring it in by using .external. So in that case, it's going to tell the assembler that the symbol is already defined in another file. Okay. And so the linker, its job is to search it's going to use the other file symbol table and then bring that into my program image or my object file. to resolve the symbol and complete the code. So it's going to link before it loads, right? So when you load your program with another file, it's going to link before it loads. And that's the process. Okay. So for 9, it says using LC-3 assembler, what type of files are generated for Windows system? And you would see that we would see a lot in our case, if we're a PC user, right, you would see that it's as executable, exe. So you would build it as an executable. Now, depending on the language, so for example, Microsoft ASM, there's an option for you to convert that assembly file after you have tested it and build the object file. You can convert that image to an exe. And with that, right, the PC user can double click the exe and it will launch. And this is what you see with a lot of like the simple executable file that doesn't require a lot of installation, right? In the process of installation, Microsoft uses MSI. So, you know, they would write the wizard for the MSI, and then the MSI bring in all the components for the executable into the system. And then for 10, you can put down like this. I put down, see page 7 and 8 of your notes. They talk about the tips when loading multiple object files. We mentioned that it should not be overlapping, right? And then for the last question, it says describe loading and linking processes when using multiple LC3 object files. For loading, it's a way to copy the executable image into the memory. And for linking, it is a way for us to resolve symbol between independent object files. And so we can use them together as a program. So in a team environment, sometime that you would have each developer work on independent object files, right? Assembly code, and then build the object files, and then eventually use them together by using .external. So I would have a main program that's gonna pull in the other two. Let's say I have 3 developers working on it, and that main program is gonna use .external, right? File 1 and .external file 2, and I just gotta make sure that those files are stored together with my main program. Okay. Just like how when you do import, if it's not native to that programming package library, you have to download it, right? You would use your IDE to install the package or the module, and then be able to incorporate it by using import, or in C++, that will be include, or yeah, and then, whether it's a .h file or something else, CPP. So the compiler handle a lot of the symbol conversion for you, like, declaration of identifier that's used, especially if they're using pointer, it points to a certain memory address. So it creates that table on the low level, and then be able to associate that with specific identifier that you use. And then when it compiles it, it push it on stack. So for assembly, we see this as a manual construction of the program, and we simulate it to see what happens in the low level, which is what the compiler sees. Any question? Okay, so I'm gonna stop the lecture here. We wrap up a little sooner than usual. I'll stick around for some questions. Okay, let's stop recording.